Hello, everyone. In this video, we're going to continue our work in section 2.1 of our workbook notes, where we go through an example to check our understanding. So in this situation, we are told to let D of T, just function notation here, represent the temperature in Denver, Colorado, measured in Fahrenheit, T hours after midnight. So we have this table here, and let's just take a moment to reflect and make sense of this table. So in the first row, we have time, and again, in hours after midnight. And then the output is going to be the temperature in degrees Fahrenheit. So number one asks us to find the average rate of change in temperature between 6 a.m. and 3 p.m. So we're given an interval of time over which we want to find the average rate of change. So at this point, I'd like you to pause the video and try to respond to this question on your own. And when you're ready, we will pick it up together. All right, so after you've had a chance to think about this and do some of your own work, let's just recall that average rate of change in temperature would be represented by the following. So for us, we'd want a change of temperature. So we could represent this with D of B minus D of A over B minus A. So what's the interval that we're looking at? Well, 6 a.m. to 3 p.m. So what would that be in terms of time, T for us? Well, T is hours after midnight. So we'd want to first convert, what is 6 a.m.? How many hours after midnight is 6 a.m.? Well, that would be 6 hours after midnight. Then what about 3 p.m.? How many hours after midnight? Well, at 12 p.m., noon, we'd have 12 hours after midnight. So then 1 p.m. would be 13, 2 p.m. would be 14, 3 p.m. would be 15 hours after midnight. So we want to know the change or the average temperature change from 6 hours after midnight to 15 hours after midnight. So for us, the rate of change that we would want would be D of 15 minus D of 6 all over 15 minus 6. And now we can read from our table what those outputs are, what D of 15 and D of 6 are. D of 15 being 71, D of 6 being 68. And then in the denominator, 15 minus 6 would be 9. So we can subtract. And the numerator, we get 3. Denominator, we get 9. Which if we simplify becomes 1/3. But we don't just have a number 1/3, we have some units on this number. So our numerator was change in temp. Our denominator was change in time. And our change in temp was degrees Fahrenheit, time was hours. So this unit here, or this the units on 1/3 would be degrees F per hour, or degrees per hour. So then if we want to make sense of what this measures or what this means, we'd say that the average temperature change is 1/3 of a degree per hour. The average rate of temp change per hour in Denver, Colorado is 1/3 degree. Per hour. So now let's take a look at number 2. And again, I'd like you to pause the video before continuing. Number 2 asks, when did the temperature change at a faster rate? Between 9 a.m. and 11 a.m. or between 11 a.m. and 3 p.m.? Justify your answer. So to help you get started, what we need to do is to compute the average rate of change across the interval 9 a.m. and 11 a.m. and above the interval 11 a.m. and 3 p.m. So go ahead and pause the video and do that now. All right, so now let's check your answers. So what is T from 9 to 11 a.m.? Well, T would be 9 and 11. And then what about between 11 a.m. and 3 p.m.? Well, T would be 11 at 11 a.m. and 15 at 3 p.m. So let's compute these two average rates of change. So I'll say from 9 to 11, average rate of change would be, well, what's happening at 11? D of 11 is 82, minus D of 9 is 77. Now our denominator would be change of times. So 11 minus 9. So we can do that subtraction, 82 minus 77. That would give us 5 in the numerator, and 11 minus 9 would give us 2 in the denominator. So that would be 5 halves, or 2.5 degrees per hour. So that's the average rate of change across that interval from 9 to 11. So now let's compute the average rate of change over the next interval. So for us, we have the interval from 11 to 15, or T equals 11 to T equals 15. And so the change of temperature at 15 would be 71. Change of temperature at 11 would be 82. Then our denominator would be 15 minus 11. So we can compute that difference of the numerator, 71 minus 82. Notice now here we're going to get a negative number. What does that mean for negative degrees? That just means our temperature went down. So it went from 82 to 71. So we see that temperature decreased. So we do that difference, we get negative 11 in the numerator, and in the denominator, we get 4. So here we have negative 2 rather, and 3/4 degrees per hour. So what we just computed is the average rate of change over the interval 9 to 11, and over the interval 11 to 3 p.m. So the question asks, when did the temperature change faster, or when did the temperature change at a faster rate? So we want to see, well, which rate is larger? So what we notice here is that if we just compared sizes, negative is smaller than a positive. But we actually consider faster rate. We don't care about the sign of these rates. And why is that? Well, if we slow down really fast, that's going to be faster than if we sped up slower, right? So it doesn't really it doesn't matter the direction of our change, just the sizes of our change. So formally, what we'd want to compute or compare is the absolute value of these two rates. And we see that the absolute value of this negative 2 3/4 is 2 3/4. Absolute value of 2.5 is 2.5. I don't know where that 4 came from. 2.5. So the larger rate, or the faster amount of change of degrees, would be at the second interval from 11 a.m. to 3 p.m. And so we could write that faster on the interval from 11 a.m. to 3 p.m. And I'll write that so it's complete in your notes. Faster change in temp, faster average rate change in temp from 11 a.m. to 3 p.m. Larger magnitude or absolute value of average rate of change. One notation to emphasize here is that sometimes average rate of change is just abbreviated AROC, average rate of change. All All right, so now let's look at the next problem. So the next problem asks us to estimate the instantaneous rate of change in temperature at 9 a.m. So what we can do for this problem, because we're not given a function of temperature, we're just given temperatures at these discrete chunks. The way to find or best approximate the instantaneous rate of change at a certain time is to find the average rate of change over an interval containing that moment that we're interested in. So we want to know that average rate of change at 9. So to do that, what we can do is to find the average rate of change on the interval that we're given containing 9. So for us, we want to find the AROC on the interval from 7 to 11, because that's an interval of time containing 9 a.m. So feel free to pause the video and work out that average rate of change on your own, and then we'll compare answers. All right, and when you're ready, let's look together. So we compute our d of 11 minus d of 7 over 11 minus 7. So consulting our table, d of 11 is 82, d of 7 is 69. Then our changes in time, 11 minus 7 would be 4. So if we compute that difference in the numerator, we get 14 over 4. So we could simplify here and we'd get 3 2/4 or 3.5 degrees per hour. So the change in temperature is 3.5 degrees per hour, approximately, our best estimate at that instant at 9 o'clock. All right, and our final problem here on this section, number 4. Let f of x be the function x plus 2 squared. Put the following in order from least to greatest. So we have 4 different rates here that we want to compare. Average rate of change over the interval -5 to 1, average rate of change over the interval -3 to 4, then the instantaneous rate of change at x equals -3 and at x equals 4. So for us, we can compute at this point the average rate of change over these 2 intervals. And we're going to be discussing methods for finding an approximate instantaneous rate of change at a given point. One method or one tool that we can use is a graphing calculator or an online graphing calculator to compare the slopes of secant lines, that is these average rates of change, versus the slope of tangent lines, which would give us an indication of the instantaneous rates of change. So let's look at a graph now. So what I'm going to do is navigate over to my Desmos app on my iPad, and I'm going to put in the function that we want to graph. So I'm going to use y as my output, y equals x plus 2 all squared. So here's a picture of my graph. And so now what we can also do is look at the secant lines between the points over which we want to find the average rates of change. So navigating back to our notes here, we want to look at the slope of the secant line above the points -5 and 1. So to do that, we want to know, well, what are the values of our function at -5 and 1? So if we plug in -5 into our function, I'll just write this out in detail here. So f of -5 would be -5 plus 2 squared, which is going to be equal to -3 squared, which is 9. And then for 1, f of 1 is 1 plus 2 squared, which is 3 squared, which is also 9. So we want to look at the slope between the points -5 and 9 and 1 and 9. So what do we think that slope will be? Let's take a look. So just moving over to a picture of our graph that I snapped for us. So here's the graph of f of x equals x, and we have x plus 2 all squared. And now average rate of change between the interval -5, about here, to 1, which is here. And again, we just computed those were both 9. So our secant line is the line between those 2 points right here. So what's the slope of that secant line? Well, we could compute out all the algebra, 9 minus 9 over 1 minus -5, but we get a 0 in the numerator. So that whole fraction just cancels out or goes to 0. So our secant line here would have a slope of 0. All right. So now the next interval, or maybe we should just keep track of this. So average rate of change over this interval is 0. Average rate of change over the interval -3 to 4. So we can just look over to our graph to find this secant line. So at -3, our graph is here, or the output, f of x, is about here, at about 1. And at 4, our output is way up here at 36. So now the average rate of change will be the slope of the secant line between these 2 points. And so we can compute that slope by finding the difference of the outputs. So for us, that would be 36 minus 1. Oh, so that's again change of y over change of x's. So 4 is our output, or input rather, negative minus -1. Oops, rather minus -3. So let me just back up a moment. So we carry out that quotient, 36 minus 1, we get 35. 4 minus -3, we get 7. And 35 over 7 becomes 5. So our average rate of change over this interval is 5. In other words, the slope of that secant line is 5. So making note of that, we have a 5 here. So now let's consider the instantaneous rate of change at x equals -3. So instantaneous rate of change is going to be the slope of the tangent line at that point. So we can do our best to approximate that by hand by finding that point on our graph, -3 to 1. Oh, I can even change that. Didn't know, new feature, new function of my iPad. Okay, anyway, back to topic here. We can find that point, -3 and 1. And we want to find the tangent line at that point. So what we can do is best approximate that tangent line by drawing a line that just crosses the graph at that point. There we go. Moving my slider a little bit as necessary. So now I'll just label this tangent line. So tangent line at -3, 1. And so to find the slope of this tangent line, again, to find the slope of the tangent line, we can just pick 2 points on our line, and we're just estimating here because we want to be able to compare these 4 rates. So I've identified the point, -3, 1. And over here, this is -10. And about, let's see, we can see how high this point is. It's about at 18. So I've identified 2 points on my tangent line, and I just want to find the slope between them. So to do that, I'll zoom in here. So I just want to find the slope between these 2 points. So I could call this point my first point, so x1, y1. This point, x2, y2. So we get change of y's over change of x's. So we get 1 minus 18 over change of x's, -3 minus -10. So that becomes -17 in the numerator over -3 minus -10 becomes -3 plus 10, which is 7. So we can approximate this. This number is about 2.5, a little bit less, so -2.4, we'll say. And so again, we're just kind of estimating here too. We really want to compare these rates rather than find the exact instantaneous rate. All right, but we'll keep note of that over here in our notes. So instantaneous rate of change at x equals 3 is about -2.4. All right, so now we just need to find the instantaneous rate of change. So I'd like you to pause the video and find this for yourself. So just to get you started, what you'll want to do is draw a sketch of this graph for yourself, or else draw the image on Desmos, and then find, or first rather, draw that tangent line at x equals 4 and compute the slope of that tangent line. All right, so your tangent lines should look something like this. So we have the point 4, 36 on our tangent line. And I found another point approximately on our tangent line here, 0 and -10. So the slope of this tangent line would be as follows. So difference in y's 36 minus -10 over difference in x's 4 minus 0. So we get 26 in the numerator, 4 in the denominator. And when we simplify here, we get about, or actually precisely 6.5. So the instantaneous rate at x equals 4 is 6.5 or 6.5. So now if we want to put these rates in order from least to greatest, in this case, we do put the negative instantaneous rate first. That's going to be the smallest. Though it's not the slowest or least fast, it is the smallest rate of change here. So if we put the letters in order, we'd start with C, followed by A, followed by B, and then the largest rate of change would be D here. So if we're just considering what the fastest rate is, then we just are concerned about magnitudes of the rates. But if we want to know the smallest to the largest rates, then we are concerned about the specific quantitative comparisons. And so something that we can observe here is we can also look at the slopes of these lines on our graph that we had just drawn, and we can compare the steepness as well. Compare steepness. And we can see that the graphs that are steeper, or the lines that are steeper, have that higher rates than the graphs that are not as steep. All right, so please take a moment and review any parts of this video to further develop and check your understandings. Thank you for watching.